Okay, it's 5:30, so let's go ahead and get started today. All right, good evening, everyone. How's everyone doing today?
Good. How are you, Professor?
Good, good. Yeah, doing well. I know it must be getting busy for you guys, so I appreciate you guys still coming to some virtual lectures. Okay, so the plan for today is we're going to finish up our MATLAB script that we started last time. So if you don't have it open already, go ahead and open up MATLAB and open up the starter script that we started. So I think we got a decent amount through, but I think we were at the part where we were about to apply boundary conditions. So if you can start up MATLAB, you can have the slides open too, but I'll share that on my screen as well. If you can do that, then you know then we can start from there. Okay. Besides that, are there? Oh, I've also posted the study guide for the midterm. So if you look at the week 5 or week 6. We're in week 6 on the Canvas site. You should see a link to the midterm study guide. So you go ahead and take a look at that. Okay. And then I still plan to do the pre-recorded review session. But what I like to do for my midterm reviews is that I try to make them as useful as I can for you guys. So usually with these midterm reviews, I don't like to cover absolutely everything, just because I'd rather cover just 2 or 3 topics in depth. And I'd like to choose those topics to be the ones that the classes usually, just in general are struggling with more. And so what I've opened up on Canvas is a poll. So if you go to the quizzes section of the Canvas site, you should see a poll there for the midterm review poll. And I've basically listed all the topic areas that are going to be covered on the midterm. And so if you could vote on the poll sometime before, I think the poll closes at midnight tonight or 11:59 p.m. So you can vote on that poll before the end of the day. Then tomorrow I'll use that information to do the review. Okay. And if you kind of forget what I expect during in each of those topic areas, you can look at the study guide, and the study guide is broken up between those different topic areas too. So what I would suggest is first download the study guide, read through the study guide, and see which learning objectives and which topics were most uncomfortable, and then vote for those in the review. So the midterm review is it's not going to be in our lecture, so I'm going to pre-record it. And so tomorrow morning, basically, I'm going to, based on the poll results, I'm going to just record a video. It'll be like an hour 15 minutes long of just a midterm review, and I'll post it up on YouTube for you guys to view for your studying this weekend before the midterm on Wednesday. And so on Monday, actually, the plan is to do another ANSYS activity. So that's going to be our second activity with ANSYS. But the midterm review I'm going to have separate from the lectures. And I do that just because with the review, I think on the one hand it would be nice to do it in the class just so that you guys can ask questions, but with the pre-recorded like this, you kind of go back and kind of replay the parts that you're confused about. Okay. Right. So Monday's lecture won't be on the midterm. So Monday's lecture, actually today's lecture won't be on the midterm either. So the midterm will just be mostly just hand calculations. So if you can refer to homework 1 and homework 2, which is due on Monday, that's pretty much what the midterm is going to be like. So there's going to be no MATLAB outside of just solving a system of equations, which all of you have been doing on the homeworks. There shouldn't be any MATLAB programming. So the stuff we started last time and the stuff we're doing today are not going to be on the midterm. Okay. All right, so go ahead and take a look at that. Vote in the poll before the end of the day, and then I'll record the midterm review tomorrow. Okay? I also posted solutions for homework 1. I think you guys probably got an email to see that the grades were posted for that as well. So you can go ahead and take a look at the grades. I left comments on your homeworks just on anything that kind of stood out to me. And so I don't know if I talked about it in this class, but the way I'm grading the homeworks this semester, just because I have a lot more students this semester than I'm used to. I'm mostly getting your homeworks for completion, but I am checking one problem on the homework for correctness. And so that question, I'm not going to tell you ahead of time because otherwise, because I want you guys to try hard on all the problems. But basically, what you'll see on my comments is that I graded one of the problems for correctness, and that's the primary correctness score you get for that. And then the rest, and then the other half of the points is based on completion. So that's how you kind of interpret the homework comments. Okay? So the solutions for that are posted on Canvas, and you can find that on week 6 of the site too. Okay. All right. Any questions on that before we get rolling today?
Professor?
Yep.
If you have any question regarding to homework, can we ask you in your office hour?
Yeah. Yeah, absolutely. Yeah, the office hours are you know, they're designed for that too. So you know, if you have questions about the homeworks or anything, you know, it doesn't even have to be about the class. Like if you, I'm always happy to answer questions about, you know, if you want to go to grad school, or if you want to do like a project, or you know, I mean, you guys are already in grad school. I mean, go on for a PhD, you know, career advice too. So office hours are for just, you know, to talk about anything. If you want to talk, I mean, I'm always down to talk about, you know, sports and other stuff too. But if there's other students there, I have to prioritize, you know, the work-related stuff. But yeah, office hours are, you know, for discussing anything. And if there's no more office hours before the homework is due, you can feel free to send me an email as well. Or if you're on the Discord, you can private message me on the Discord too. And I've been pretty responsive on that as well. So any way that you can to contact me, go ahead and use that. But just don't call my office phone, because I haven't set up, I have not set up call forwarding on my office phone yet. So just email, Discord, or office hours. Those are usually the best ways to reach me about any questions.
Okay, thank you very much.
Yep. Okay. All right, so if there's any other questions, definitely just stop me anytime. Don't be shy to turn on your mics, because I'm going to be sharing my laptop screen, and I'll see the chat, but it's usually a little bit more delayed than when I'm using my iPad. So, okay, so hopefully everyone has MATLAB open, so let's go ahead and get started. Okay. Okay, so here's the script that we were working on last time. And so if you remember from last time, we kind of filled out a lot of these upper portions. So we filled in, first of all, we defined the size of our problem by defining the number of elements and the number of nodes, right? Actually, let me remind ourselves about the problem that we're solving, which is right here. Okay? Then we defined how the elements are connected with each other. So we defined this connectivity matrix right here. Okay? And then from there, we specified all the properties of the elements over in this section here. Okay? And then throughout the script, this is the example problem that we're basically going to be solving. So this is actually an example we did in the lectures. And so, you know, the reason I chose this was so that, you know, we're solving this problem in a very different way. And so, you know, it's usually nice to do a problem that you know the correct answer to, just so you can verify that the code works. So this is usually kind of a good way, especially when you're developing new code. You want to solve a problem that you kind of already know the answer to, just to kind of help you verify, you know, that is correct. Okay. Oh, let me ask a question first. So I haven't modified the text on this MATLAB script. So is everyone able to read the text on the MATLAB window okay, or should I make this a bit larger?
The size is good.
Okay. Okay, so I'll keep the size the same then. But if it ever gets too hard to see, just let me know, and I can always make it big. Okay. So let's get back to it. So you know, we were on the boundary conditions last time, right? I think where we left off was on this slide right here, talking about this index system. So remember, you know, when we're solving these you know, finite element problems, especially for beams and for frames, and actually for 2D trusses too, you know, the size of our global stiffness matrix is much greater than the number of elements in our system. So in this case, we have 4 elements in our system, right? So we have, or 3 elements, sorry, 3 elements and 4 nodes. But you know, our global stiffness matrix is actually going to be 12 by 12. And the reason for that is that at each of the nodes in our system, we have 3 degrees of freedom. So we have an x displacement, a y displacement, and a rotation for node 1, and the same for nodes 2, node 3, and node 4. And so when we're setting our boundary conditions, if you remember when we were doing this by hand, you kind of manually went into the corresponding rows in our global stiffness matrix in order to specify those boundary conditions. Okay? And so the whole point of this next section for the boundary condition index is to tell the program, to tell MATLAB which rows that we need to modify. Okay? And so we have this this index system right here, where, you know, we can compute the index for, you know, the corresponding x displacement, y displacement, and rotation for the node labeled I. Okay? And so the way that we're going to use this equation is that if we want to specify a boundary condition on the x displacement of node 2, all we have to do is just use this equation right here and plug in I is equal to 2, and then that will give us the index in our matrix. Okay? And so I just had a simple example here. So let's say that we want to you know, apply boundary condition on the y displacement of node 3. And so we would look at the second equation here, which is the index of IY, and then plug in I is equal to 3, and then we get 8. Okay. And so if we go back to our example problem, let's just consider just the Dirichlet boundary conditions first. And so the Dirichlet boundary conditions, remember, correspond to the constraints in our system. And in this particular problem, we have fixed constraints on nodes 1 and 4. Okay? And remember, when we have fixed constraints, that means all 3 degrees of freedom, x displacement, y displacement, and rotation will be constrained to 0. Okay? And so we need to compute the rows in our global stiffness matrix that we need to modify that correspond to the x, y, z, or x, y, and rotation degrees of freedom for nodes 1 and 4. And so what we're going to do is we're going to take our 3 equations from before and first apply all 3 of them at I is equal to 1. Okay, so with I is equal to 1, we get 3 times 1 minus 1 plus 1 is equal to 1, and then 2, and then 3. Okay, and then we're going to specify or compute the indices for the same thing for node number 4. So the same the same 3 equations, but with I is equal to 4. Okay, and then we get these list of indexes here. So we get 1, 2, 3, 10, 11, 12. And remember, what this tells us is that we're going to modify the first, the second, the third, and the 10th, the 11th, and the 12th rows of our global stiffness matrix. Okay? And then what we need to do now is we need to put this list of numbers into this variable right here called Dirichlet BC index. Okay? And so I named this this variable just to kind of specify, this is the list of indices that we want to apply Dirichlet conditions. Okay? And so the way you're going to do this is you're just going to do a simple list separated by commas. Okay? And so, for the first 3, we're just going to do 1, 2, 3, and then we're going to do comma 10, comma 11, comma 12. Okay. And so we have 6 entries in this vector, is to tell us that we're going to apply boundary conditions on these 6 indices. Okay. And so go ahead and fill that in if you haven't done so already. Okay. And then and so I'll say at this point, we haven't magically applied our Dirichlet boundary conditions yet. This is just kind of specifying the information that we need for it later. So actually, at the bottom of this code right here, we're actually going to use this information to actually modify our global stiffness matrix. But at this point, we haven't even formed our global system yet. And so we're just basically identifying the rows that we need to modify. Right? And so, I think one common comment that I might get is, why are we specifying it up here if we're not even going to use it until later in the code? And so this is, and so the reason I do this is I structured this code very deliberately, just to make sure that we can put all of our inputs at the top of the code. And so anything that we're inputting in terms of the properties and the boundary conditions, all of that's going to be input up here. And so the idea for that is that, if you want to use this code or you want to ask someone to use this code, you can tell them that the only things that you have to input are just the top few sections of the code, and then everything else from there will work automatically. And so this is kind of just a usability kind of thing, just to kind of make it easier to use. Because what I find is that, if I'm having kind of a fairly complex code like this, and I have to input something on line like 176, I think that's really easy to forget. And then you come back, especially after a few weeks, and you use the code, and you don't exactly remember how to use it, and then you kind of forget to set something, halfway down, 3/4 down the code, and it just becomes a nightmare to kind of debug and see what's going on. So when I write these codes, I really like to front load all of the input information, just so you can put that at the beginning, and then everything else after that, you don't really have to worry about. Okay. All right, any questions on this? Okay. Okay, so that's the Dirichlet boundary condition. So we need to do the same thing for the Neumann. So you can see for the Neumann boundary conditions, I've created another vector right here called Neu BC index. Okay, and so we're going to do the same thing here, is we're going to specify the degrees of freedom where we want to specify a Neumann boundary condition. Okay? And so for this particular problem, we had 2 loads. And so the first load that we had was a horizontal load on node 2. And so this is this corresponds to the row which is associated with the x displacement on node 2. Okay? And then we're also going to apply a moment on node 3. And so this degree of freedom corresponds to the row of theta 3. Okay? And so the next I want you to fill in this vector right here, and then I want you to use the same formulas up here as here. Okay? And so remember, for the Neumann boundary condition, you want to use the x displacement of node 2. So you're going to use this equation with I is equal to 2. And then for the moment on node 3, you're going to use this third equation with I is equal to 3. Okay? And so you go ahead and plug those in. And so we plug in I is equal to 2. We get 3 times 1 plus 1. So this is going to equal to 4. So that's our first index. Okay. And then our second index is going to be 3 times I minus 1, which is 2. So 3 times 2 plus 3, which is going to be 9. Okay. And so this tells us that we want to apply Neumann conditions on row 4 and row 9 of our global system. Okay. But you know that we're not done with the Neumann boundary condition yet. And so the next thing that we need to do is we need to also specify the values of those Neumann conditions. Okay. And so we specified the rows, but remember for the Neumann condition, we actually have to put the value of the load on the right-hand side matrix. So in this case, we have a horizontal load of 10,000 pounds, and then we have a moment that's equal to 5,000 pound-inches. Okay? And so similarly, we need to fill in the values of these loads into this vector right here. And so first, let's do 10,000. So we have 10,000 just like that. Okay? And then our moment has a value of 5,000. And it's really important that when you're, especially if you plan to use this, you can definitely use this script for the homework too to help you out, just to help verify your answers. You know, it's really important that the order on which you put this index and this load value here, the order has to be the same. So the first index here, you know, you put the load that's applied on that index in the first slot for Neu BC value, and then the second index has the second entry here, and so on and so forth. Okay, so remember the order of that is really important. And you'll see why later, just how we implemented this. Okay. Okay. Are there any questions on the Neumann boundary conditions? Okay. Okay. And so the next portion of the code, you actually don't have to fill in anything because I've already filled in these for you. But in this section of the code, you know, what I've done is I basically created storage containers to hold all of our matrices for the problem. Okay, and so we have 3 kind of categories of matrices. So the first thing that we need is a matrix to store our global stiffness matrix. Okay, and so I've called this matrix called kglob, right? And you can see here I'm using the zeros command to basically create an empty matrix, so a matrix of all zeros. Right? And the inside this zeros matrix, you can see I've specified the size. Okay. And so, you know, the size of this matrix is going to be a square matrix. So the number of rows is equal to number of columns. And the size of that is going to be equal to number of nodes times 3. Okay. And remember and so the reason we do that is because for each node, we have 3 degrees of freedom. And then that's going to be the size of our matrix. So in this case, we have 4 nodes. And so we have 4 times 3 equals to 12. And so our global stiffness matrix can be 12 by 12. All right, next we have the global forcing vectors. You can see we call this fglob, and so the size of this is just going to be a column vector. And so just like we saw in the previous one, we have n nodes times 3 for 3 degrees of freedom per node, and then the number of columns is just 1. Okay. Okay. All right. So the next thing that we create is something to store all the element stiffness matrices. Okay. And so in this next section here, we're going to compute all the element stiffness matrices, but we need a way to kind of store that information. Okay? And so when you're doing these problems by hand, you know, the way that you store the element stiffness matrices was you just simply wrote it down on a piece of paper. And so we kind of need to do the same thing for MATLAB. But the way we do that in MATLAB is we kind of create data storage containers for it. Right? And so this, you might not have seen kind of a zeros command used like this. And actually, you know, before this class, you might not have even seen the zeros command before ever. But you can see here, I've kind of made a three-dimensional array. Okay, and so it's not just a matrix, but it's a 3D matrix. Okay, so think of this like if you're familiar with the term like 3D chess, this is kind of the same thing. So you can kind of think of it's like a chessboard is kind of like a grid of boxes. You can think of that, right? But if you do 3D chess, the way you do that is you kind of stack boards on top of each other, and this is kind of the same thing. So for each of the element stiffness matrices, we're going to stack each of them on top of each other, and that's how we're going to refer to them. All right, so there's a comment in chat, a fiber array. Okay, all I've never heard that term before, but I'm guessing that's what this refers to, is an array of matrices. So that's basically what this is. So yeah, if you're familiar with the term fiber array, that's something good. Right? Okay, and so you can see from this that the size of this element stiffness matrices, element stiffness, first we're going to do 6 by 6, right? And so we know that for each of the elements in our matrix, our element stiffness matrix is going to be a 6 by 6 matrix, right? And so we have 3, and that corresponds to 3 degrees of freedom for each of the 2 nodes in our stiffness matrix, okay? And so we have 6 by 6, and then the third dimension here is going to be the number of elements in our system, and that's corresponds to the fact that we need 1 element stiffness matrix for every element, okay? Okay. And so I've come up with an analogy here. So besides the chess boards that are stacked on top of each other, you can also kind of think of this as kind of like a file drawer. Okay? And so a file drawer, if you've seen one before, basically is you pull out the drawer and each of the different files has papers in it. Okay? And so I make this analogy because you can think of each file in the file drawer to be an element stiffness matrix for that element. Okay? So our first file will contain our element stiffness matrix for element 1. Our second file will be the element stiffness matrix for element 2, and our third file will be the element stiffness matrix for element 3. And so, that's kind of just another analogy to kind of help you visualize what this K element is. Okay. Okay. Any questions on this?
I didn't get how you define the size of the array for the stacking of the stiffness matrices.
Sure. Yeah. So the sizing is kind of like this. So first we have to do 6 by 6, right? And so this expression right here that I've highlighted, this is actually the element stiffness matrix for the frame, right? So it's a 6 by 6 matrix, and we're actually going to be filling in all these entries here in code, which is what this next big chunk is for, right? And so that's where the 6 by 6 comes from. And then the third dimension here is the number of elements. And so what that says is that we're going to have 1 element stiffness matrix for every element in our system. And so what we're going to do here is we're going to basically loop. And so we're going to visit the first element, define the element stiffness matrix for that element, store it into this file, you kind of think, and then move on to the next element, compute the element stiffness matrix, store in that file, and then so on and so forth for as many elements as you have in the system.
So we have like for example, for this example, the number of elements is 3. So we have 3 6 by 6 matrices.
Exactly, right. So you can think of it as 3 6 by 6 matrices that are stacked on top of each other.
Stacked on top of each other. Got it.
Yeah.
Thank you.
Mm-hmm. Yep. All right. Any more questions on this? Okay. Okay. And so that's all the preparation. So this is probably, I think, when you're first starting to code, this part's actually really important because, you have to define all the data structures and you have to define all the parameters for your problem. And I think, when we're doing problems by hand, we do a lot of that kind of implicitly in our heads, or we kind of just automatically kind of write it down on paper. But when you're doing programming, you have to be really, really explicit about every single parameter and every single data structure that you're going to use for the program. So, I know I spent a lot of time on this first section right here, but this is really, really important, because without this kind of structure and without this infrastructure in place, it's going to be really hard to do this. And the thing with coding is that it's a little bit, I know it's annoying to define all these things and to kind of organize things in a certain way, but it really pays off in spades when you're developing later, because an organized code is a code that's a million times easier to debug, and it's a million times easier to read. So it might be faster just in the moment to just write a code really quickly just to get the job done. But if it's code that you anticipate to use many times over and over again, it really pays to put in the work up front to make it organized, and first of all, just use variable names that make sense to you, and label everything, comment everything, because it really, really helps a ton. And so for this code, I tried my best to add as many comments and to kind of walk you through the process as much as I can. And so when you're writing your own codes, definitely try to do the same thing. All right, so the question. So decomposition operation should be the same with 2D matrices because they're all placeholders because of the non-commutative nature. Let's see. Yes, yeah. So yeah. So all of these, even though these are kind of 2D structures, they should all follow the same rules of traditional matrices. So you can add matrices together, and you can it follows all the same rules as long as you kind of do it properly. So MATLAB's really good about that. So MATLAB really designed this language to really mimic kind of the mathematical rules that we kind of know from textbooks and stuff like that. So as long as you follow all those rules, and do the syntax correctly, it should follow everything like that just fine. Okay, and so now let's actually go ahead and compute. And so we're going to enter this kind of big chonker of a loop right here. And the reason this loop is so big is because the element stiffness matrix for a frame is actually really big as well. Okay, and so let's kind of break this down. Okay, and so if you remember, when we're doing these finite element problems by hand, we would compute. I would always ask you guys to compute the element stiffness matrix for every single element and write them all down. Okay, and so we're going to do basically the equivalent of this, for in MATLAB. And so, to do that, obviously we need to do this. We need to do this computation, one for every element. Okay, and then for a code like this, where we don't know how many elements that we could be, at least a priori, right? And so in this case, we know that we have 3 elements, but we want to be able to use this code for something that has like 10 elements or 12 elements, or 20 or 30 or something like that. Okay, and so we want to make this code basically as flexible as it can. And so the way that we can do that is we can use a for loop. And so a for loop, as we kind of remember from the very beginning of the class, a for loop is a coding construct that lets you repeat a set of instructions as many times as you want. Okay, and so you can see in this line right here in line 67, I've defined a for loop to go to start at 1, and then it's going to end at the number of elements. So this loop is going to repeat itself, 1 for each of the number of elements that we have in our system. Okay, and so using a structure like this is really useful because say if we wanted to use a bigger system, and we say that we have 5 elements here, then the rest of the code is basically going to automatically update, and we don't have to change anything. Okay, and so that kind of goes back to that first comment that I made about when you do a different problem, all you have to do is kind of just change this upper portion right here, and then everything kind of below this compute comment right here doesn't have to be changed. Okay, and so. And so this next bullet point right here is, just the fact that since we're doing a frame element here, the element stiffness matrix is 6 by 6. So we actually need to compute all 36 elements of this matrix. So it's going to be a little bit tedious to do this at first because 36 is a lot, but I'll kind of walk you through it. Okay, so let's jump into the loop. And so the first thing that we need to do in the loop is that we need to retrieve the material properties for this element. Because if you remember from the beginning of the code, we've set this code up such that each of the elements in our system can have a different property. And so first of all, the first thing that's kind of obvious that comes to mind is the angle for the element, right? And so if we look at kind of the example problem here, right, you can see that every element is angled at a different angle, and we've specified this here on this theta property here. So this first element right here is rotated 90 degrees, and so we've set the theta prop to be pi over 2, right? If you plan to use cosine, I think someone made a comment last time using cosine d sine d. If you want to do that, you can specify this in degrees. Okay. Element 2 right here has an angle of 0, and then element 3 is actually rotated all the way around, and so it has an angle of 3 pi over 2, or 270 degrees. Okay. And so the first thing we need to do is we need to retrieve the angle for this element, and we also need to compute the sine and cosine of that element, right? And so the reason I do this is because sine and cosine are going to show up a ton in these computations, and so just like we have here in this written form, I'm going to shorten the cosine and sine of the angle by c and s. Okay, and so you can see here I've defined the variable c to be the cosine of the angle of this element. Okay, and so the way that we're going to retrieve the angle of this element is we're going to refer to that entry in the vector. So remember, theta property here is a vector which is sized, which has a length equal to number of elements, and so we want to get the angle for this particular element. And so the way that we do that is we, call name for theta property, and we say that give me the entry that's in this slot right here. So in this case, this slot is has the index I element, where I element here is our loop index. Okay, and so the first time around this loop, I element is going to be equal to 1, and so that's going to give us the first entry in theta prop. The second time around in the for loop, I element is going to be equal to 2, and so that gives us the second entry in this vector, and so on and so forth. Okay? And so you're going to see me use this this loop index quite a bit. And you know, the loop index is a really great tool because it really allows you to choose the elements for that particular entry in the vector. Okay, so does this kind of make sense about how we, first of all, how we retrieve the theta property for this element, and then second of all, how we compute the cosine and the sine of that angle?
The theta property is the angle that we defined in the beginning, right? Like 0, 90 to 270 degrees, kind of like that. Okay.
Exactly right. Yes. Yeah. So so theta property, that's it's a list of all the theta values for each of the elements in our matrix, in our system. Sorry. And so if you go back up here, so you can see element 1 here has an angle of 90 degrees, or pi over 2. Element 2 has an angle of 0, and element 3 has an angle of 3 pi over 2. Yeah, and so we're basically getting those values and using them in this computation.
Thanks.
Okay. Okay, and so just like just like for the thetas, we also need to retrieve like the Young's modulus, the area, the moment of inertia, and the length, and then that's what I'm doing right here. So I'm defining these variables where E is equal to E prop at IL, so that retrieves the Young's modulus for this particular element. A is retrieving the area for this particular element, so A is equal to A prop at IL, okay? And then I is equal to I prop at IL, and L is equal to L prop, okay? And so now that we're done with this part, we've gotten all the properties that we need for this element. So we have the cosine of the angle, the sine of the angle, the Young's modulus, the area, the moment of inertia, and the length, and we're now ready to start computing the entries in the matrix, okay? Okay, and so that's this next section right here. And so, you can do these entries in whatever order that you want, but for me, it makes the most sense for me to do it row by row. Okay, and so let's look at the first row in this matrix first. And so let me zoom in here actually a little bit, just because we're going to be spending the next few minutes filling these in. Okay, and you can see here what I'm doing is I'm defining the values in this matrix kind of one entry at a time. Okay. And so the way that we're going to do this is we're going to refer to K element, because remember K element was our data structure to store our element stiffness matrices. Okay, and then in this matrix I'm going to go to the entry 1, 1, and so 1, 1 is going to be this entry in the matrix right here. Okay, the top left, right. This next part is essential. So this part is basically saying that this is the 1, 1 entry for the first element. Okay. And so remember our analogy of the different element stiffness matrices stacked on top of each other. And so we want to do it for this particular element. Okay. And then after that, I've written in the variable expression here. So you can see from the left-hand side here. And so this is going to be A times cosine squared plus 12 times I divided by L squared times S squared. Okay. And so that's the formula that we're going to fill in for that. Okay. Next, we go to the 1, 2 entry, and then we see that the entry that we put in is A minus 12I over L squared times cosine times sine, okay? And so that matches up exactly with this right here. Okay? And you can verify, so definitely check my coding, just to make sure that I've input every formula that's correct for this first row. Okay? So we have minus 6I over L times S, minus A cosine squared plus 12I over L squared times S squared, minus A minus 12I over L squared times cosine times sine. Okay, so it looks okay to me. And so that's the entire first row of this matrix. We started with 1, 1, then we went to 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. Okay, and so you can see, I've done the first row for you, and so what I want you to do now is to fill in the rest of the rows in the matrix. Okay. But before you set about doing that, you can see that I've leveraged the symmetry of the element stiffness matrix here. Okay. And so you can see, once I go to the second row of the matrix and I start to work on element 1, 2, and so that's row 1, 2, traditionally here we have a blank space because this is equivalent to the entry at 1, 2. Okay, or 2, 1 is equal to 1, 2. And so that's what I basically specified here. So I'm saying that the entry at 2, 1 is equal to what we've already input for 1, 2. Okay, so I'm basically leveraging the symmetry just so I don't have to, do a lengthy equation here. And you can see I've done this for the third row just to kind of give you another example of what that looks like too. So the entry in 3, 1 is equal to the entry in 1, 3. Okay, and then the entry in 3, 2 is equal to the entry in 2, 3, which is this guy right here. Okay, and so I'll give you guys a few minutes. I want you to go ahead and fill in the rest of this, everything that's to do here for the entries in the matrix. Okay.
Professor, I have a question.
Sure, what's up?
Why we started with element 2 and not with element, the first element? Because
oh, you mean
we need it in our glue bar system, the element 1 or first 2, that's right?
Yes, yeah. So in the slides, I have this at element 2 because I drew the arrow coming from the second file here. But in reality, you're right. So we need this for every single one. And so this loop is actually going to automatically do that for us. So it's going to do the first entry, the second entry, and the third entry. But I said this was just for element 2, just for this analogy where I'm pointing to the second file in this cabinet right here. But in reality, every element is going to have the same formula here. But this element 2 right here just refers to the fact that I'm pointing to this second file right here. So this element 2 up here doesn't mean anything. It's just to refer to the picture. But what I want you to do now is just to kind of fill in all the formulas for each of the different entries in the element stiffness matrix.
Okay, thank you.
Yep. Mm-hmm. All right, how's everyone doing on inputting those values? You good, or do you need some more time to do that? Okay, yeah, a couple more minutes. Oh yeah, that's true. Yeah, MATLAB also has a symmetry value or symmetry function as well. Yeah, so you can definitely use that as well for this. Oh, I had it on this page too. Okay. Okay. So hopefully everyone's had it. So has everyone finished writing the entries in the matrix now? It's a lot. I know. It's it takes a while.
I'm too slow.
Well, it's if you're still catching up, I think it's okay. I just want to you know, make sure that we get to the end today. If there's time at the end, I think you know, you can work on it a bit more too. But
Okay, I think that works better. I'm
okay.
too slow. Yeah.
Okay. Yeah, it's yeah, it takes a while. Yeah, this part definitely takes quite a bit of time, because these are not really trivial expressions here. But you know, hopefully everyone kind of gets the idea. And you know, even though I know this is really tedious, but it's you know, it's the nice thing about this is that once you kind of input it in, and granted that there's no bugs, which can happen, this is only something that you have to do once, because once you've input these instructions into the code, then every time you do a frame problem from here, then this program will basically automatically compute that for you. So you know, that's kind of the idea with a lot of these finite element codes, and just kind of computational physics in general, is that it's a lot of work up front to develop the code, but once you develop the code, you can use it for so many different problems. And ANSYS is kind of like a really great example of something like that, which is, you know, I'm sure it took them years to develop ANSYS, but like now it's developed into this thing where, you know, so many people use it, and it's such a useful tool for everyone. Okay. And so I want to kind of comment on one thing before we leave this this loop, and it's the fact that, you know, if we look at our element stiffness matrix here, you know, we have this E over L factor that's in front of the matrix. Okay. And so before we exit, we need to multiply the entire thing by E over L, which is basically what I'm doing right here. Okay? And so, you know, I point that out because, you know, I want to point out this kind of special MATLAB notation that maybe you've seen before, but maybe you haven't. But I know that I didn't learn this notation until actually pretty far in grad school too. And so when you have a data structure like this, which is like, you know, it could be a matrix, or in this case, it's a fiber array. You know, there's sometimes you want to perform an operation on every single element in one dimension or another. Okay? And so one way that you can do this is you can write a loop to do it, you know, which is fine to do. But a faster way that you can do it in MATLAB is to use this colon notation right here. Okay? And so you can see for our element stiffness matrix up here, you know, we refer to each dimension individually, right? So we have 1 through 3 parameters for this K elm. Okay? And so if we want to apply something on the entire, you know, first dimension and our entire second dimension, instead of putting a number in here for the index, what we can do is we can just put a colon there. Okay? And the colon will basically apply this operation to everything in that dimension. Okay? And so in this particular case, we want to multiply a constant factor by everything in the 6 by 6 portion of the matrix. So we're going to put colons for the first entry and for the second entry. Okay? And what we're going to say is that this 6 by 6 matrix, which is, you know, denoted by these colons, is equal to the proportionality factor multiplied by the same thing with the same factors right there. Okay? And so if you've never seen the colon notation before, that's basically what it does. It says, give me every entry in this dimension right here. Okay? And so we're going to use this again later once we're specifying the Dirichlet boundary conditions. Because remember, for the Dirichlet boundary conditions, we need to replace it as an entire row in the matrix. And so using this colon notation makes it actually really simple to do that. Right? Okay. Question. Oh, the question is, does that bring in the scale factor to each component of the matrix? That's correct. Yeah. And so what that does is that it's going to take every, all 36 entries in our 6x6, and it's going to multiply by E over L into that matrix. Yeah. Yeah. So it's a shorthand notation to that. So like another way that you can do it, of course, is that you can just modify all the entries up here and say that just going to multiply this by E over L, right? And so that's another way that you can do it. But if it's something that you're going to apply for the entire matrix, you can kind of do it in just one line, just like this. And this is kind of a nice feature of MATLAB. I think you could probably do something similar in Python, but I think the syntax may not be as convenient. So this is a kind of a nice thing for MATLAB to do. Yeah. Okay. Okay. So at this point in the code, we've computed all of our element stiffness matrices. So we've kind of gotten through that part of the problem, right? And so if we refer back to, the way we usually solve these things, the next step is to assemble the global stiffness matrix, right? And so I'll say that this, out of everything in this code, this is probably going to be the most confusing thing to do. So definitely, bear with me on this, but it's, this kind of saves you a lot of time, okay? And so if you think of assembly, the way that we did it was that we looked at each element stiffness matrix, and we looked at the nodes that it works on, and then what we did from there was we slotted in the entries of the element stiffness matrix into the global stiffness system, according to which entries that were there. So we're basically going to be doing the same thing here, but in code. Okay. Okay. All right. So the first thing that we need to do is we need to launch into another for loop. And you can see here that we have a for loop just like we did before. And so we can see we have a for loop that loops over all the elements. So for IL is equal to 1 to number of elements. Okay. And the reason we're doing this is that we're going to slot in the element stiffness matrices kind of one by one, just like just like we usually do. Okay. And so the first thing that we need to do is we need to find out which elements or which nodes that this element is connected to. Okay. And that's what this section of the code does right here. Right? And so we're defining these two new variables, n1 and n2, and these are going to be the nodes that are going to be connected to this. Right? And so remember, at the very beginning of this code, we defined a matrix called connectivity, and so that connectivity matrix basically specified which nodes our element is connected to. Right? And so the first thing we need to do is we need to retrieve the first column for this row. Okay. And so we're going to go to connectivity at IL, comma 1, okay? And so that gets us the first node that this element is connected to. And then we need to get connectivity IL, comma 2, and that's going to be the second node that this is going to be connected to, okay? Okay? All right. And then after we've retrieved those nodes, we need to find kind of the row and the column that we need to modify in the global stiffness matrix, okay? And so to do that, we're going to use the same formulas that we did before. Okay? So if you remember when we were doing our boundary conditions, we had these formulas here to specify, the row in the global stiffness matrix. Okay? And so the way that we use this formulas, remember, was we plugged in the node number in for I right here, and then we multiplied by 3, and then we added 1. Okay? And so these are going to give us basically the starting points to add the entries into our global stiffness matrix. Okay? And so you can see I filled in the first one for you. So the first one, we're just going to start with the index for the x component. And then from there, we're just going to simply add 1 or add 2, depending on what entry that we're doing. Okay. And so you can see here, I've gotten the row for the x displacement for node 1. Okay. And so what I've done right here is I've done 3 times n1 minus 1, which is this first part right here. And then I've added just 1 to that. Okay. And so what we need to do with this part is we need to kind of fill in that same expression for node number 2. Okay? And so we're just going to copy the same formula. So we're going to do 1 plus 3 times n2 minus 1. Okay? And so that gives us the starting index for node number 2. Okay? And so this is basically going to point us to the row for the x displacement for node number 2, and that's IND2 right here. Okay. And so at this point, what we need to do is we need to retrieve the element stiffness matrix that we computed for this element before, okay? And so we're going to define a new variable called k underscore e, and what that's going to be equal to is k element, where k element is the that fiber array that we just computed, okay? And we need to get the 6 by 6 element stiffness matrix for that element, okay? And so you can see we're referring to this k element vector. And we're using the common notation again. So we're saying that get everything in this first dimension and get everything in the second dimension. And then we're going to refer to just this particular element IL. Okay. And so the result of this is simply just going to be a 6 by 6 matrix. Okay. All right. So does this kind of make sense to everyone? Is this first part of just retrieving the node numbers, computing the index, and then retrieving the element stiffness matrix for this element? Does that kind of, are there any questions on that? Okay. Yeah, so remember, this is definitely, I would say the most difficult part of this code, because there's a lot of just indices and different numbers and references that you need to keep track of. So definitely, take your time going through this code. You'll have the lecture videos and you have the slides. Definitely kind of go slowly through this part, because it's it's difficult. I know. And when I was developing this code for the first time, I had to kind of redo this part over and over just to make sure I was doing it correctly too. Okay. And so now what we need to do, so now that we have the proper indices and now that we have the 6 by 6 element stiffness matrix for this element, we need to slot these into the proper locations into the global system. Okay. And so I'm going to do this in quadrants. So I'm basically going to do this in 4 code segments. Okay. And so if you kind of refer to this figure on the left right here, what I'm showing you here is our element stiffness matrix, and I've split it up into 4 different quadrants. So I have the top left quadrant, the top right quadrant, bottom left, and bottom right quadrant. Okay. And then so the reason I did this is so that we can put these into the correct parts. Okay. And so you can see the reason I did this, because the top left quadrant right here has, refers to u1x, u1y, and theta 1, and this is u1x, u1y, and theta 1 for the rows right here too. So everything in this top left coordinate, top left quadrant, the columns refer to node 1, and the rows also refer to node 1. Okay, and so if you look at this top right quadrant, you can see all the columns refer to node number 2, but the rows refer to node number 1. And then, so on and so forth for these two. Okay? So the bottom left quadrant is columns node 1 and rows node 2. Okay, and then bottom right coordinate is rows and columns node 2. Okay. So questions. So this is the nested for loop equivalent of nesting I comma j. Yeah. So you can definitely do this with the nested for loop too. But I wanted to keep the structure of the code just by looping over the elements. So that's kind of why I have this right here. And so you can definitely, do this with the nested for loop as well. But I, just to kind of split this up and to kind of make it a bit more clear, I've kind of opened it up a little bit to just have just one loop. Yeah. Okay. And so what I've done right here is I've filled in the top left quadrant for you. Okay. And so, whichever nodes correspond to which quadrant, that's going to be really important. Okay. And so, let's look at all of the entries that I've specified here on the left-hand side here. Okay, and so you can see everything here refers to IND1, right? So remember, IND1 is the row that corresponds to the first node in our element. Okay, so you can see here everything is IND1. So IND1, 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 IND1. Okay, we're going to be adding different values to this because we need to add into the different the different entries in these quadrants. But I kept it simple so that I made everything IND1, IND1. Okay. Okay. And so you can see right here that, just from this first line, I've used kind of this update notation here. So what I'm saying is that k glob at IND1, IND1 is equal to k glob at IND1, IND1 plus ke at 1, 1. Okay? And so what this is saying is that at this entry in the global stiffness matrix, we're going to add the 1, 1 entry in our element stiffness matrix. Okay? And then, the next line right here is going to be k glob at IND1, IND1 plus 1. Okay, so this is the the row and the column that's associated with that, and so that's going to be like this entry right here. Okay, And so to that, we're going to add our element stiffness matrix at 1, 2. Okay. And then so on and so forth for 1, 3, 2, 1. And so you can see here, I've to refer to the different degrees of freedom, I've added quantities right here. Okay. And you can see, if you kind of think of this as kind of the base case up here, where IND1 is IND1 is equal to K1 at 1, 1. Then whenever I added 1 to the index right here, I've also added 1 to this index right here too. So when I added +1 to the second entry here, then I've also added 1 to this KE right here as well. Okay, and so you can see that trend is kind of consistent all throughout. So when I add +1 to the row entry, you can see I've added +1 to the row right here too. Okay, and you can see I've kind of followed that trend all throughout here. Okay, so then let's go to the next quadrant. So this is going to be the top right quadrant. So going to be this guy right here. Okay, and so remember, for the top right coordinate, the rows are going to correspond to node 1. And so you can see here I have IND1 for all the first entries for this global matrix right here. Okay, while the columns are going to refer to IND2. So that's node number 2 right here. So all the columns here will have IND2. Okay. All right. Okay, and so I did the first 3 lines right here. So you can see I'm still using the same update notation. So I'm going to say that K glob IND1, IND2 is equal to K glob IND1, IND2 plus KE at 1, 4. Okay, and so you notice here that I've started the second one at 4 instead of 1, and that's because I'm using IND2 right here. Okay, so there's kind of a 1-to-1 correlation right here. So anything right here that says IND1, the corresponding entry for KE is going to be 1. And everything that starts at IND2, the corresponding entry is going to be 4. Okay, and then when we add 1 to these, we're also going to add 1 to these guys right here. Okay, and so I'll give you guys a few minutes. You don't have to fill in everything, but just make a little bit of progress and kind of fill in at least maybe for the top right quadrant and the bottom left quadrant for these guys, and it follows just kind of the same structure right here. But while people are filling that in, are there any questions on this one? Yeah. So I know that this part is really difficult to understand. Because it's a lot of things you kind of have to keep in your head, and I always kind of take this part for granted, because I've been writing these kinds of codes for a lot of years of my life now, so a lot of these kind of come really kind of easily to me. But I remember when I was seeing these kind of data structures in this format for the first time, it kind of just went way over my head. So and the hard thing is, like, it's not the easiest thing to kind of explain too. So definitely take your time, and if you're completely lost with this, it's definitely okay to say that too. And we can go over this again and again until we have to. So assembly is always kind of I think if you're coming from a computer science background, like, assembly is not that hard to it's a little bit easier to get, because you're dealing with a lot of loop indices and stuff like that. But if you're not used to programming a lot, this can be really intimidating to do. So so definitely, if this kind of seems like just an enigma right now, don't worry about it. We're going to come back to this kind of code over and over and over throughout the semester, and it's definitely pretty hard. Let me turn on the light because it's going to get dark. Oh, question. All right, so the question is, the structure of inputting into the global system, oh, thank you, should work for any structure given that there is another cross-section. Yes. So again, this is a similar thing where, once we've implemented this part of the code once, we don't have to do it again. So if we have a different structure to our system, say we have like 5 elements, or the elements are connected differently, this part of the code will update automatically. And so that's kind of the nice thing. So, once we're done with this code, the only thing that you're going to have to update is just kind of this top portion right here, for updating the properties and updating the boundary conditions up here. Everything else is gonna be taken care of automatically for you. So that's why, when you're developing this part of the code at first, it looks really obtuse, just because I'm trying to leave things really as general as possible, just so it can handle all these different cases. But but the benefit in doing so is that it becomes like a really flexible code that you can use it to solve for basically any 2D frame problem. Yeah. And so actually, you know, once you kind of finish developing this code, and after a few days, I'll post my solutions for this too. But don't wait for that. Definitely, you know, implement it yourself. You can actually use this to check on your homework too. And so that's actually what I did for, you know, when I was developing the solutions for problem 3 in the homework was I used this code. And I know the question everyone's asking is, you know, can you use this code for the midterm? You can try, but I'm going to write problems such that you can't use this code for the midterm. So, you're welcome to try, but it's not going to get you the right answer.
I have a question.
Sure. What's up?
So about someone's question. So someone asked, this is the nested for loop equivalent of listing I and J, something like that.
Yep.
What does it mean?
Right. So what he's referring to by that is a nested for loop is like a for loop within a for loop. And so I think we did one practice like this, or you had one problem like this on ANSYS activity 1. And so a nested for loop would look something like this. So we have like a for loop within a for loop.
Oh, yeah.
Yeah, so
Okay,
this is pretty common for matrices because, you know, matrix is a 2x2 structure, and so to visit every entry in the matrix, you know, this is another way that you can do it. So you just have a for loop. One of it goes over the rows, one of it goes over the rows, the other goes over the columns. And with this, you can visit every entry. So actually, you know, so the person that's asking, you know, he's taken me before for another finite element class, and so we've used a nested for loop for that before because, you know, we're basically visiting every single entry in the element stiffness. But I thought I'd do it like this just to kind of open up the logic a little bit more, just so you can kind of see it a little bit. Because with the nested for loop, it's really compact in terms of the number of lines, but it gets really hard to kind of understand what's going on. So
yeah, that's basically what I do with the example that you gave, like on first week or so, I just kind of opened it up to understand what basically it's doing. So it can be written that way too, right? So you can just like do two nested for the one nested for loop, like two inside. Okay.
Yeah. So that would definitely be another way that you can do this too, and it would definitely make this a lot more compact. So you could probably do this in like maybe half the lines or something, or maybe even less than that. But yeah, just for kind of educational purposes, I opened it up just so you can see me, you know, manually doing every single entry in the matrix like that. Yeah.
Got it. Thanks.
Okay. So I'll give you guys maybe a minute or two if you're still filling these in, but I want to make sure that we cover the boundary conditions before we end today. But boundary conditions are compared to assembly are relatively a lot simpler. So, you know, assembly is definitely the most difficult part of this code. Yeah, so there's a comment in the chat that said 3D sounds like a mess. It is a mess. Yeah, so for 3D, you know, unfortunately, you can't really open it up like this because it just becomes, you know, your codes are going to be like tens of thousands of lines long. So you kind of have to use nested for loops for like 3D problems. So it becomes a little bit more difficult to understand. But that's kind of why we're sticking mostly to 2D in this class. And actually, your final project too is actually going to be 2D as well. So yeah, I've been thinking a bit about the final project, and I think it's going to be fun. I think you guys are going to like it, but it's going to be a lot of this stuff. Okay. So hopefully, everyone had a chance to fill in a little bit of this matrix. But again, you can definitely come back and do it and fill in the rest later. I think, a lot of people are still kind of filling in the element stiffness matrix from up there too. But I do want to get through the boundary conditions before we go. But you can see here, these pieces of code are not nearly as bad. Okay. All right. So then now that we've assembled our global stiffness matrix, if we kind of go back to our manual process, the next step to solve these problems is to assign our boundary conditions. Okay? And so let's start with the Dirichlet boundary conditions. Okay. And so remember, for the Dirichlet boundary conditions, the way that we assign them is that we make an entire row equal to zeros, and then we put a 1 on the diagonal. Okay? And so let's write the code to do this. Okay? Okay, so if you look into the starter code, so you look at this line that I've highlighted right here, okay, you can see that I've listed another for loop, okay? And so, for loops are great because it allows you to repeat a set of instructions, but you can leave the bounds of the integral kind of arbitrary, and that lets you repeat an instruction basically as many times as you want, okay? And so let's look at the upper bound for this for loop right here, which is the length of the Dirichlet boundary condition index array, okay? And so basically what we're saying is that this for loop needs to repeat, and the number of times it repeats is equal to the number of Dirichlet boundary conditions that we have. Okay? And so in this particular problem, we have 6 Dirichlet boundary conditions that we need because we have 2 fixed conditions. And so we need to apply a Dirichlet boundary condition on row number 1, row number 2, row number 3, row number 10, 11, and 12. Okay? And so this for loop right here is gonna loop over 6 times. Okay. Okay. And so let's kind of break this down. So the first thing that we need to do is we need to retrieve the row. So we need to know what row are we even working on. Okay? And so to do that, we're going to reference this Dirichlet BC index array. And so we're going to say that this new variable ind index underscore Dirichlet is equal to our Dirichlet BC index at this IDIR. So that's going to be the loop index right here. Okay? Okay, so now we know that what row in the global stiffness matrix that we're working with, okay? And so the first thing that we need to do is we need to zero out this entire row, okay? And so the way that we're gonna do that is we're gonna refer to our global stiffness. So this is K glob, which is the thing that we just finished specifying up here, okay? And so, we need to go to the proper rows. And so the row, remember, is given by this INDDIR, okay? And so again, we see this colon notation here. So what this is saying is that, go to this row in the matrix, but then give us all of the entries in that row, okay? Right? And then what we need to do is we need to set this equal to 0, okay? And so it's tempting to kind of say that this should just be 0 right here, but in reality, what it should be is a vector that, oops. Oh, 1. Yes, it should be a vector that has the same length as the row in that matrix, okay? And so the way that we're gonna do that is we're gonna use our zeros commands. Remember, our zeros command creates a vector that's all zeros, okay? And we're gonna set it equal to zeros at 1, n nodes plus 3, or times 3, okay? And so what this does is that it defines a vector of zeros that has 1 row and has the number of columns equals to n nodes times 3, because that's the size of our global stiffness matrix. Okay. Okay. And then the next thing that we need to do is to set the diagonal value equal to 1. Okay. And so the diagonal entry is given by INDDIR, INDDIR. Okay. And this is going to be equal to 1 right here. Okay. All right. And so that's that's how we basically assign this. So this row, this line of code right here is going to zero out the entire row by replacing that row with just a vector of zeros. And then this line of code right here puts a 1 on the diagonal entry. Okay? And then this is just for for sanity's sake, but just to make sure, we need to make sure the right side of the equation is equal to 0, and that's kind of all I did right there. Okay? All right. Any questions on that? Okay. Yeah, so pretty straightforward. So I mean, the only thing that may be new is using the colon notation, which remember lets us grab the entire row, so all the columns in that row. Okay? And then we're going to do the exact same thing for the Neumann boundary conditions. So you can see here we have a similar structure for the loop. So we can see that for I noise equal to 1 to the length of Neu BC index. So this will loop, this loop will repeat equal to the number of Neumann boundary conditions that we have. And so in this case, we have 2 Neumann boundary conditions. So this loop is going to repeat twice. Okay. And so the first thing that we're going to do, just like we did for the Dirichlet boundary condition, is we're going to retrieve the index for that Neumann boundary condition. And so we're going to refer to this entry in the vector. Okay. Next, we also need to retrieve the value. So we need to retrieve the value of the load at that node. Okay. And so we're going to define a variable called val Neu, and this is equal to Neu BC val value at the same loop index right here. Okay. And so now we know the row in which we want to apply the Neumann boundary condition, and we know what value to put in. And so all we have to do is we have to put this into our global forcing vector. Okay. And so the row of the global forcing vector, we've already just retrieved that. So it's going to be ind Neu. And then the value that we're going to put there is going to be just equal to val Neu, just like that. Okay. All right. Any questions on the assignment of the Neumann boundary conditions? Okay. All right. And so now that we've, assigned our boundary conditions, the next step is just to solve. Okay. And so the nice thing about this is that, I know when you guys are doing the problems manually, you had to manually input each entry in the matrix. And so the nice thing here is that it's already kind of in MATLAB already. And so the only thing that we have to do is we just have to invert those matrices. Okay. And so our global stiffness matrix here is K glob. And then it's going to be inverted by F glob. Okay. And so you can use this this backslash notation. I've seen some of you guys in the homeworks do this. Okay. Okay. So you can just use the inverse function in MATLAB. So that's totally fine as well. Okay. And so all you need to do here is to just basically solve the system of equations. So you can do basically anything that you want. Okay. And so for, I like the backslash just because it's compact. And it's kind of it's one of those smart MATLAB commands that can choose basically the best method for you. And then from here you run the code, and then just like you've done in your homeworks, this vector right here you solve for U solution is going to contain your deformation solution for this problem. Okay. All right. Any final questions on this code?
Can you post what the solution is once we fix everything and plug everything in?
Yeah. So I have the solution right here. Okay. And so actually, this is actually the solution to one of the homework problems. So I think this is the homework 3 part B, I believe. And so you can see me kind of fill in everything in this matrix right here. So I'm gonna fly through it quickly. Just because I want you guys to actually fill in those parts, but I'll post this after a few days, just so you can have it as a reference. But I do want you guys to try to actually fill in the rest of the codes yourself. Okay? And I know what some people will do at this point is that they're going to go to the YouTube video and play it at like 0.25 speed just to see all the entries. So feel free to do that as well. But I think you get the most benefit from doing this by, trying to implement it yourself first, and then going back to check the solutions after that. But yeah, I'll post my solutions to this after a couple of days.
Thank you.
Mm-hmm. Okay. And so that's the frame code. Okay. And so one other thing that I want you to work on. So this is going to be part. This is not going to be part of this homework. But next week, we're going to be doing another ANSYS activity. And at the end of that ANSYS activity, what I want you to do is to implement another finite element code, but instead of a frame, I want you to implement a code for a 2D truss problem. Okay? And so you're going to use a very similar structure to what you have here, except it's going to be for a 2D truss instead of a frame. So actually, the 2D truss is a little bit simpler just because the element stiffness matrix isn't as big, but it should provide you good practice because it's it's not something that that we're going to walk through together. So so definitely start thinking about that. Definitely finish up this frame code first, and then start thinking about how you would use this kind of structure of the code to implement a 2D truss. Okay. Okay. And so with that, that's all we got time for today. Oh, question. So so it will return 12 values, correct? Yes. Yeah. So when you run this code for this particular problem, this U solution here should be a 12 by 1 matrix, or 12 by 1 vector. Sorry. Yeah, because it's the displacements and rotations at every single node in this mesh, which is 4 nodes. Yeah. Okay. So that's all we got time for today. So it's 6:45. So thank you everyone for tuning in. I know it was it was a lot to take in, but definitely refer to the slides. I tried to make these slides as kind of step by step as I could. Refer back to this video, and hopefully that will help you guys implement this code. Okay. So the question. So is the midterm still next week? Yes. So the midterm is going to be next Wednesday. So so definitely. If you weren't here at the beginning of class, I posted a poll onto the Canvas site where you can vote for the topics that you're most uncomfortable with. So definitely vote in that poll, and then tomorrow I'm gonna film a midterm review session to basically help you guys studying, and I'll post that on YouTube for you guys to have too. But yeah, the midterm will be next Wednesday. Okay, you're welcome. All right.
I have a question. Can I ask it?
Yeah.
Mm-hmm. So someone mentioned again about using like a symmetry function, something like that, instead of manually inputting the symmetry elements there.
Yeah. Mm-hmm.
How can we do that?
I think probably let's talk about that offline, because it's okay. I'm actually not sure myself. I know that the function exists, but I'm not sure how to actually use it. So let's talk offline about that.
Okay, got it. Thank you so much.
Yep. Yes. So the midterm will be a 24-hour exam. So I'm going to post it at 5:30 on Wednesday. So we're not going to have lecture next Wednesday. So I'm just going to post the exam, and then you'll have 24 hours to do it. So and so you can open and close the exam as many times as you want. So you can kind of think of it as kind of like a short-term homework assignment. So as long as you upload the exam before 5:30 on next Thursday, then it'll count. Yeah. Mm-hmm. All right. So thank you, everybody. So definitely you guys are free to go, but I'll stick around if you guys have any more questions. So have a great weekend. Vote in the poll, and then I'll see you guys on Monday. Yes, vote, definitely. Everyone vote.
Hello, Professor.
Hey.
I had a question for the frame part. When we were doing the stiffness element matrix, the first row, the K underscore element 1, 2, I underscore EL,
yep.
is that the 0, or is that the, I forgot what that was.
Or let me see, let me share my screen again. And so you're referring to basically this part of the code right here too, right?
Yeah, so for like the second row element stiffness, that first line 88.
Line 88, yes. Oh, so you're asking if this is 0?
Yeah.
No, so it's not. So it's remember, because when we're doing the element stiffness matrix, it's symmetric, and so so basically you can kind of think of it as all these entries in the top right here. They get reflected over here. So they don't fill in, usually, unfortunately, in the book, they don't fill in all the entries for this matrix. But in this particular case, it's symmetric. So this entry right here is going to be equal to this one. And that's what I've kind of shown you right here, where 2, 1 is equal to 1, 2. Yeah.
Oh, okay. I see that now. And then is that going to be also the same for the stiffness matrix?
Yes, exactly.
Okay.
Or not for the global stiffness matrix. You have to be careful, because it's because after you apply the boundary conditions and everything, it's not going to be symmetric. So the only time we're going to apply this symmetry is when we're constructing this element stiffness matrix.
Okay.
But when we're doing the assembly, we kind of have to follow this format right here, where we kind of add each entry kind of 1 by 1.
Okay, thank you.
Yep. Mm-hmm. All right, do you guys have any more questions?
No, I'm just leaving, sorry.
Okay.
Thanks.
Yeah, no problem. Yep.
Thanks, bye.
Bye. right, good night, Scott.